Right, so moving on to chapter 7. So last lesson will have been the end of chapter 5. Now moving on to chapter 7 is a continuation from chapter 5 about forces and direction. Now this chapter is where the real deal begins. You're going to incorporate everything you've learned in chapter 5 into here or chapter 7. Now, chapter 7, all of them are examinable. Okay, so chapter 1, chapter 7.1 to 7.6, they're all examinable. We'll mainly break the sort of the whole chapter into 3 parts. The first part, where these two are, the first one are static particles. So equilibrium, static particles. So I don't know, static particles. Okay. 7.3. Now you will see randomly why the 7.4 goes after 7.6. It's not that I don't know how to count. I know 4 is after 3 and 5, but strangely when I look at a textbook or the syllabus or the Edexcel textbook, I realized the 7.3 7.5 are the same thing, so I decided to teach together, and 7.4 is something not relevant to 7.3 and 7.6. Therefore I do it different ways. Now you can actually tell by you see how I group them nicely. Look at the topic. 7.3 to 7.5, 7.3, 7.5, and 7.6, they're all inclined plane. This one pulleys. So these two are just inclined planes. So inclined planes with particles. So not I mean particles. So particles. Now, why do I stress out the word particle? Because 7.4 is a chapter on its own, which is about bodies. Oops, wrong way, wrong line. Bodies. So technically, the whole section, the whole chapter is very exam heavy, but it's divided into 3 parts. So the particles, inclined plane, and bodies. We'll talk about the difference between particles and bodies later. But essentially, in the first 2 parts, the 7.1 to 7.6, apart from 7.4, we're going to use the same method that we used from before, which brings us to here, the notes for 7.1. The first 3 steps. So before I go through a set of particles, let's go through 3 steps. First, you draw a force diagram that includes the forces on x and y directions, and then resolve any forces. To be honest, that should be the first part anyway. Resolve the forces that have not been included. It means breaking into x and y direction. We talk about that in 5.3 and 5.1, 5.2. Next, step 3, we're going to use F equals ma in both directions. You're going to consider in x direction and then consider y direction. Depends, sometimes you might want to consider y direction first before x. But essentially, you're going to use F equals ma in both directions. All right. So what's static particles? Static particle is particles in equilibrium state. So what does equilibrium mean? Equilibrium means not moving. So upward force will equal downward force. Leftward force will equal rightward force. All right. So example in here, find P such that the particle is in equilibrium. So equilibrium, right? So it means the upward force equals downward force. The leftward force equals the rightward force. All right. So let's follow 3 steps in here. First step, we're going to resolve any forces that are not on the axis. So if you use a pencil, that's your axis, and you realize the the P Newton is not in the axis. So step 1, we have to resolve the P Newton, resolve P Newton. Now, if you are familiar with resolving, you probably don't have to draw the whole, draw a new axis. I'll just go through again. To resolve the forces, I'll draw a new pair of axes. That's my P Newton. You can, and then there's a 45-degree in there. Next, I'll make a right angle triangle with the x-axis. So here we go. And to make a P Newton going bottom left corner, I need to go on x to the left and y underneath. So resolving means writing x equal. So x equals, using trigonometry, P cos 45. 45 is a sort of a nice special value, which is root 2 over 2. So root 2 over 2p. And y is P sine 45. That's sine 45 is also root 2 over 2p. So if you're familiar, you can also do it on the diagram. So on diagram, you can also do it right here, basically. X and y like this. All right. So don't forget the p in the x. Don't forget the p after the x and y. Step 2, force diagram. So force diagram means we draw one big diagram that include all the forces. So from the question, we have, I know my writing's not the best. This is 20 on the top. So 20 upwards and 20 rightwards. We've also resolved p in the different directions. So x going left is √2/2p. So let me do a bit of highlighting. So that's √2/2p goes here. Now, because that's the x going to left, and then this √2/2p will go, can you guess? It'll be downwards in here. Why? Because why, pun intended, not unintended. Anyway, y going downwards. So going downwards in here is √2/2p. That would be your. Okay. So next step, we normally use F equals MA. Now, if you use F equals MA, I'll just show you. So if you use F equals MA in x direction, first, x direction, so 20 subtract √2/2p. Like the moments, you do one side, take away the other. So I do the right side, take away the right side 20, take away the left side, which equals the mass. We don't know the mass, but we know the acceleration is 0. Why 0? Because equilibrium. So A is 0, right? So equilibrium A is 0. Now imagine if you multiply by 0 on the right hand side, you do some rearranging. So move the √2/2p, this one here, to the right hand side. So you get 20 equals √2/2p. So essentially what you can see in here is the rightward force equals the leftward force. That's equilibrium. Is that not what I said in the beginning? When you say equilibrium, it means the left equals the right, up equals down. Now, we don't have to do up equals down, because if you try to up equals down, you'll see the same equation, 20 equals √2/2p. So, right, so then we just solve p, so 20, so p equals, if we divide 20 by √2/2, then you get the answer. We tend to write as a decimal, which is 28.3 Newton. Right, I write to 3 SF. So I'm not going to do the y direction. I know the steps tells me do F equals MA in the y direction, but I don't have to in here. Right? Next one. The diagram shows a particle in equilibrium under the forces shown. By resolving horizontally and vertically, find the magnitudes of the forces P and Q. Now this time you're given the axes. All right. So maybe first question for you is, how many forces do we have to resolve before putting into the force diagram? The answer would be 2, because the 4 Newton and the P Newton are not on the axis. So we have to resolve the 4 Newton and the P Newton. Now, if the diagram is given to you, you can do it on the spot. So I'm going to do it there. So I'm going to do a right angle triangle. That's my x to the left and y upwards. For the P Newton, I can do it here. That's x to the right and y upwards. Right? Remember, the x and y direction will have to give you the final direction to the same as the force. For example, the 4 Newton pointing to the 4 Newton here pointing to top left means we have to go left and go up. P Newton to the top right means go right and then up. All right. The direction of the x and y matters, because in the force diagram, if you put the x and y direction in the wrong place, you will have the wrong equation to solve the F equals ma, which lead you to the wrong answer. All right. It's like you try to push someone and you end up pulling someone, or pushing a door, you end up pulling a door when you say push. So that's the same thing. Right. So we need step 1. We resolve 4 Newton and P Newton. Okay, so let's resolve the 4 Newton. So 4 Newton first. So using SOHCAHTOA, now I will draw the triangle in here, but you don't have to if you get what we're doing here. X and Y, so that's 45 degrees, and that's 4 Newton. So on the X, using trigonometry, X will be 4 cos 45. For the calculator, you should get 2√2. Y is 4 sine 45. For the calculator, you should get 2 Newton. All right, do the same for P Newton. This time, I'm not going to draw out the triangle. So P Newton. I'm not drawing a triangle. X under X in here is P cos 30, and Y will be P sine 30. So X P cos 30, and Y is P sine 30. We know sine 30 and cos 30 are special angle. Cos 30 is √3/2, so √3/2P. Sine 30 is a half, so it's a half P. Right? Or if you tend to use, you can use 0.5P. Right. Next step, force diagram. So we can draw a big force diagram to include all the forces. I'm good on here, so I can show you all the forces on here. So first of all, include the one that was on diagram, which is Q. Q goes going downwards. So we've done that. Next, we can't include the 4 Newton because we have to include the resolved version of the 4 Newton. So going left, we've got 2√2. 2 Newton going upwards. For the P Newton, we have to do the X to the right, which is √3/2P. And then going upwards, we have a half P. Okay. Now, equilibrium. So step 3, equilibrium means upwards. So upwards equal, actually, I should knock this off. So I'll say step 3. Okay. So upward force equal downward force because of equilibrium. Now, normally you can't do that, but you can do that because equilibrium. So we know upwards equal downwards. So upwards is 2 plus a half P. 2 plus a half P equals Q. Also, what else do we know? We know the left equals the right force. Again, because of equilibrium, the left force is 2√2. The right force is √3/2P. So clearly, we can tell the left equation, this first equation on the left side, we can't solve because there are 2 variables. The right equation, we can solve it quite easily. We can multiply 2 across and divide by √3. So P equals to 2√2 times 2/√3. Plug it in the calculator. You should get 3. In the calculator, it will give you 4√6/3, which is 3.27 Newton, around to 3 SF. Now, the reason I put a 4√3/3 in there is because when I use the value for P on the left-hand side, I need to use the full value. Okay, otherwise it will give me a rounding error in the final answer. So P is 4√6/3, so I sub it in, different color. So 2 plus a half times 4√6/3 equals Q. So again, plug the whole thing in calculator. Q equals 4.46 Newton and 3 SF. And that will be the answer. Okay, one more. Yes, you're in a tree. I'm showing one more example. This time, inclined plane. All right. Now, but for this inclined plane, you don't have to do the mg cos theta, mg sin theta. That will come later. Actually, we can resolve 5 Newton. Right. Anyway, let's go for the question. So this time, equilibrium. Here's the axes. You can see the axes on the x and y, like that. So how many forces do we have to resolve? 2 again. P Newton and a 5 Newton. So we need to resolve the P and the 5. We can resolve it on the spot. So I'll do it in here. I think that the angle must be alpha. So this will be, so x and upwards is y. Now for the 5 Newton downwards, hopefully you do sort of remember how to resolve. You can remember the shortcut for 5 Newton. For the mg in the inclined plane, hopefully you do remember that's the mg, which is the actual Newton. So mg is 5, so 5 sine 30. Sorry about this. Pen is just a really bad one. Sorry, 5 sine. It's not. I'm trying to justify my poor handwriting, but it's just really annoying to write. It's too sensitive to the board. So this one is going to be 5 cos 30 degree. So we have resolved the 5 Newton essentially. All right. So that's a shortcut. So resolving mg in an inclined plane is mg sine theta to left hand side, to left downwards the slope, and mg cos theta on the y, downwards y. All right. Why is there no g? Because the mg is the weight. The weight in here is 5 Newton, so it's 5. So mg is 5, so 5 sine 30. Right, so next we just have to resolve p. You can resolve it in here on the spot. So x is p cos alpha, and y is p sine alpha. Okay. Next, once we've done that, that means we'll resolve p. We can now do our second step, which is a force diagram. So force diagram, draw big axes. Right. So know your enemies. So on the left wing, we have not being politically pundit, but you get what I mean. So 5 sine 30 degree. Left downwards, we've got 5 sine 30, 5 cos 30 degree. My bad, it should be 5. 5 cos 30. Upwards, we've got 2 Newton. And then for the p, x, we've got going up, going right, we've got p cos alpha. And then upwards, we've got p sine alpha. Right. So hopefully that's not too much issue. Now, these steps are, people find mechanics difficult because every time when you work out a question, it's always a big question and it's building up on previous stages. So stage by stage, you need precise accuracy on your working out. So I'll just quickly go through before I go through last step. So first step, you're going to look at the axes. Any forces not on the axes, you have to resolve them. Reason that we have to resolve is so that we can compare them. Okay, so comparing is easier, it's much easier. It's only available if you have them on the either horizontally or vertically. So when they say horizontally, I mean on the x-axis. So in this question, because 5 Newton and the p Newton are not on the axis, so we have to resolve them. Resolve them means putting them back in the x and y axis. So for 5 Newton, we've learned how to resolve it in chapter 5.2. If you want to remember how to resolve 5 Newton again, you can, which is look at chapter 5.2. Okay, chapter 5.2. Essentially, is you make 5 Newton. The 5 Newton is that will be the hypotenuse, and then you resolve from there using the triangle. But if you don't want to do that, you can remember 5 sine 30, 5 cos 30. For the p Newton, quick and easy. That's your right angle in there. X going right, up, y going up. So yeah. Next step, we can put the force diagram. So make sure you don't copy the wrong thing, and 2, you don't copy the wrong direction. Third step, because equilibrium, okay, we love the word equilibrium. So equilibrium means left equals the right force. So left force equals the right force. Left force equals the right force. So left force is 8 plus 5 sine 30. Right force is p cos alpha. I'm going to simplify the left side because 8 plus 5 sine 30 looks like something we can make it a nice number. So 8 plus 5 sine 30 is 10.5, I believe. Yep. So p cos alpha equals 10.5. Next step, upwards equal downward force. Upward force is 2 plus p sine alpha. Downward force is 5 cos 30. Oops. Where am I? Sorry. Okay, 5 cos 30. Next, I want to make p sine alpha the subject. So p sine alpha equal 5 cos 30 degree. Subtract 2. I don't like 5 cos 30 subtract 2, so I'm going to put in a calculator. Make it a nice, well, not quite nice, fraction. -4 plus 5 root 3 over 2. Now, one thing to note in here, as I guess a technical thing. Let me ask you a question. Are these two fractions the same? You've got a minus outside a fraction and a minus on top. The answer is they're not the same. Reason being is because if you put a minus outside, it means if you want to put it back on numerator, you have to apply a bracket. So the first bracket essentially becomes -4 minus 5 root 3 over 2. that's not the same as the bottom. So when a calculator put the minus on top of fraction, don't be a smarty and try to put it in front of fraction. It's not the same thing. Okay, so so the -4 has to be on top. If you calculate say minus on top, so -4 is -4. Right. Next, now why do I make p sine theta alpha the subject instead of p the subject? The reason being is I can see a left-hand side has p cos alpha, right-hand side p sine alpha. If you recall trigonometry, sine over cos will make a tan alpha. So what I'm going to do is I'm going to make this equation 1, equation 2. What I'm going to do next is I'm going to do equation 1 divided by equation 2. So which becomes, so equation 1 is p sine alpha divided by the left-hand side of equation 2, p cos alpha. On the right-hand side, we've got -4 plus 5√3 over 2 divided by 10.5. Right? Now, another small technical thing in the calculator you want to avoid is that when you have a triple fraction in here, I tend to do the last bit as a division, because in here you have a fraction, the top is a fraction divided by 10.5. If you try to do this in the calculator, it won't allow, they will not see it that way because they're trying to, how would I put it? Okay, it's quite a technical thing in here, so it's a small bit, but people do not realize. Let me ask you a question. Sorry. Now, if you're not sure what I'm talking about, try to put these two lines, the green lines I drew in a calculator, you'll see a difference. The answer won't be the same. But which one is the correct one? The bottom one is the correct one. Why? Because it was the fraction divided by 10.5. What they did the first one is they are treating they're treating -4 plus 5√3, so in the bracket, divided by, so over 2 over 10.5. So it's a small technical thing, but you have to understand which one is division, which one is a fraction. So you want to do the second one, okay? So I tend to write divide by 10.5 in calculator. So next, we can then, on the left-hand side, p and p divide, sine alpha over cos alpha becomes a tan alpha. So if you understand where this step comes from, you can just on the side write in here. So tan alpha equals sine alpha over cos alpha. Identity. So equals, now the right-hand side, if you put in a calculator, you should see -4 plus 5√3 over 21. So again, I put it as a fraction is because I don't want to use decimals in here. I want to try to use the full value if I can. And then I inverse 10, the right-hand side, or arc10. You'll learn that in chapter 6 in pure maths. The proper name for this -1 is arc10. So which is, so if you put in a calculator, it will give you 12.5 degree 3SF. And that's one answer. They also want you to find P. To find P, you can either use equation 1 or equation 2. I'll probably use equation 2. Reason being is 2 looks simpler than equation 1 just because there's no fraction. You know, no one likes fraction. So sub in equation 2. So I'm going to sub this sub into equation 2. So P cos, now 12.5, you must use a full value in the calculator. So 12.5 equals 10.5. So P equal 10.5 divided by cos 12.5 degree, and you should get 10.8 Newton. Okay, all right, so, and that's it for chapter 7.1. Quick recap. Step one, resolve any forces that are not on the axis. Okay, so resolve any forces. In this example number 2 that we've gone through, 4 Newton, P Newton, not on the axis, so resolve them. Second step, draw a big force diagram, like this one. Step 3, upward force equals downward force, left force equals right force, and then usually you will solve all your variables. Now, why can we make them up equals down, left equals right? Where does F equals MA go? We're not using F equals MA. Technically we are, but we're not using it here because the word equilibrium tells us we can do that. Up equal down, left equals right. Now later in the chapter you can't do that, so it's not always equilibrium. So when you equilibrium, think of you being treated by the exam board. All right. So next lesson we are looking at 7.2, which is more with the similar thing, but this time I think it will be moving. Is it? Maybe not, but we'll see. All right.